When developers deploy autonomous AI coding agents into unpredictable production codebases, they quickly hit a ceiling. The agents encounter edge cases, make errors, and fail. Fixing these daily execution errors by fine-tuning billions of model weights is impractical. It is slow, expensive, and risks introducing catastrophic forgetting, where the model loses previously learned behaviors. To avoid touching the weights, the industry spent the last 2 years pivoting towards context adaptation, relying on automated prompt optimizers and iterative test-time memory systems. But research from Stanford and Sambanova reveals a critical problem. These standard context adaptation methods contain architectural flaws that break down as tasks become more complex. Patching language models with continuous prompt engineering has reached a functional limit. Overcoming these failures requires changing the underlying structure of how AI systems manage memory. The first major pathology is a common assumption in prompt engineering: the idea that concise, generalized instructions are inherently better for model performance. This creates Brevity Bias. Automated optimizers aggressively compress instructions, discarding the granular, domain-specific heuristics the model needs to solve a specific problem. This illustrates the contrast. On the left, an optimized prompt provides a vague instruction to write clean code. On the right is the dense JSON API parameter for pagination that the agent actually requires to function. Without that level of detail, agents fail. They cannot track Spotify pagination logic or query exact phone APIs using generic instructions. When optimizers sacrifice detail for brevity, they strip the agent of the exact operational knowledge required to resolve these tool use errors. The second pathology occurs in monolithic memory systems. This happens when an LLM is tasked with repeatedly rewriting its entire cheat sheet after every interaction. As the context expands over thousands of tokens, the model inevitably experiences attention saturation. The sheer length triggers a sudden summarization pressure. This chart plots context tokens and task accuracy on the AppWorld benchmark. We see the memory steadily accumulating, reaching 18,282 tokens and peaking at 66.7% accuracy by step 60. Then, at step 61, the system breaks. The LLM abruptly compresses that accumulated memory to 122 tokens. A red baseline appears, showing base model accuracy. After the memory crash, performance falls to 57.1%, lower than using no memory at all. Treating agent memory as a single, continuous string of text leads to this outcome. The researchers define this failure as context collapse. Agentic Context Engineering, or ACE, abandons continuous text prompts. Instead, it relies on an evolving, structured format called a playbook. The unit of this playbook is the bullet. Context is structured as a collection of discrete, immutable items rather than a loose narrative. Each bullet contains a persistent unique ID like CTX-00042, a thematic section tag like API specifications, and the actionable text content. The structure includes 2 digital counters. A helpful integer tracks successful applications, and a harmful integer tracks failures, creating a performance record for every rule. Compartmentalizing knowledge into tracked, discrete bullets ensures that new rules can be added without corrupting or deleting existing functional memory. Modifying this playbook requires breaking the workload apart. A tripartite division of labor prevents a single LLM from becoming cognitively overloaded. The generator executes tasks and reasons using the playbook. It outputs the exact bullet IDs consulted, explicitly tracing logic to solve credit assignment. The second role, the reflector, evaluates that execution against environment feedback, like Python tracebacks or API errors. Mapping errors to specific bullet IDs, the reflector tags active bullets as helpful or harmful, providing a causal diagnosis. Finally, the curator takes this analysis and synthesizes a localized delta operation, a single targeted addition to the playbook. By isolating generation, reflection, and curation, the system ensures the existing playbook remains immutable to LLM hallucinations during updates. Merging these new delta rules into the main playbook requires a way to prevent bloating the context window with duplicate instructions. The solution is the grow and refine engine. It relies on deterministic algorithms rather than LLMs, ensuring 0 hallucinations occur during the merge phase. Beginning with semantic deduplication, the incoming rule transforms into a unit vector array in high-dimensional space. the engine performs a cosine similarity check. If it matches an existing vector by 75% or more, the duplicate is rejected, incrementing the existing bullet's helpful counter. To manage growth, the system uses a budget-aware pruning mechanism. This failsafe triggers if the playbook exceeds its configured token capacity. The engine calculates a utility formula, ranking bullets by subtracting twice the harmful count from the helpful count. This evicts the worst performers from the context window. Replacing LLM-driven rewriting with deterministic mathematics creates a self-cleaning memory architecture that organically retains verified heuristics. Maintaining a 30,000 token playbook introduces a practical tension. Large input contexts are traditionally associated with higher costs and increased inference latency. That assumption overlooks the modern LLM-serving paradigm of KV cache reuse. In this paradigm, stable prompt prefixes bypass the computationally expensive prefill phase. This visual compares the two approaches. On the left, traditional prompt optimizers constantly rewrite and shuffle the prompt string, triggering a 100% cache miss. On the right, we see a massive, rigid block retaining a 91.8% cache hit. The right side succeeds because ACE strictly appends new bullets to fixed section headers without reshuffling previous text. This achieves prefix stability. The paper's evaluation of this architecture on prompt caching infrastructure demonstrated a 91.8% KV cache hit rate. Bypassing the prefill compute at this scale translated directly into an 82.6% reduction in build input token costs. Prompt engineering for complex agents prioritizes prefix stability over token counts to leverage these caching economics. This cost efficiency scales in tandem with raw performance, proven by results on the complex App World Autonomous Software Agent benchmark. This chart compares the results. An open-source DeepSeek model running the ACE architecture achieved a 59.5% average score, compared to 42.4% for the unadapted base model and 46.4% for the JIPA optimizer. This performance increase occurred in an online test time environment. The agent learned relying on zero human-labeled ground truth, adapting strictly from execution feedback. The chart expands to include IBM Kuga, a closed production system powered by GPT 4.1. The open-source ACE configuration matches its performance. And on the most difficult challenge subset of the benchmark, the ACE framework outperformed the IBM production agent by 8.4%. The data suggests that relying on monolithic prompt rewrites limits agent potential. Compound AI systems require deterministic, evolving playbooks that scale with long context economics.